It's a summation of all the discussions we've been having the last three presentations on reliability, maintainability, and later on we had carried out a stress analysis followed by the sensitivity analysis. Now I'm going to discuss about risk assessment of a particular site. Now, as you can see, you can get a view of the site view, and all these presentations I've been showing to you have been focusing on the availability of the on-site. This small part of the big picture, and we try to improve the reliability of this system in order to reliability, maintainability, and in order to improve the availability of the unit. And there are several factors which is goes beyond what we've been discussing, but the focus was on this: improving the reliability. The availability of the unit increases in a similar fashion. If you increase the maintainability, availability of the unit increases. So we can meet to the requirement of the customer, and the unit will be profitable. Now let us look into the several factors. I just go briefly because it's quite a complex task, and much of what I've been presenting here comes from my experience, and I don't have much background in academics, but I do have experience in the area which I'm discussing here, and the complexities are enormous, and to model the entire thing is quite a complex task. What we've been doing all this through the presentation is to model this small part of the plant, and you can see here there are several factors comes into picture. So you have an on-site generator, and which supplies a product to the customer for a particular application, and you have a backup just in case this unit shuts down. The backup comes into picture and supplies the product to the customer. So the customer always gets a product irrespective of the unit is running or not running. The complexity comes into picture. If you want to get a backup, the backup is not standalone. It depends on other logistical factors. Here it has to be transported. It's just I think there is some problem here. Okay. Now the logistics behind is this has to be bulk stocked in some location several kilometers away from the unit, and has to be transported. Now this is we're going to have a wait time here, because this needs to come several kilometers away. They could be 1,000 kilometers away or nearby, within 50-60 kilometers away, but it's going to take time because there has to be a stock plus and the transportation time, and of course there's going to be cost behind it. And there are other factors which comes into picture is the weather, because these plants are designed for a condition not specific to this site. So there is problem of tropical countries like tropical rain, or could be heavy snow or lightning. It could be a corrosive atmosphere if it's in a chemical process zone, a clustered chemical zone. And then you have the problem of supply chain. That is, to do maintenance of this unit, you need to wait for the service technicians to come to the site, and so there are going to be some delay from this side. We're going to analyze this part. We're going to analyze the backup supply chain part. These are going to be critical component in our analysis. And then of course there's going to be a maintenance crew, which is on the operating and maintenance crew, which needs to come from the regional office to the site, and so there are going to be some waiting time here as well. and the availability of the skilled technicians. Now, there could be another risk which is never factored so precisely, is the customer demand. What happens if customer doesn't demand this much amount of product? So they're going to be, there's a capital invested at the site, and it's not been utilized because the customer demands reduces. So they're going to be issues such as this. We're going to factor that into risk assessment, and we're going to factor the backup as well. If you're going to backup the supply chain, the service and spare parts, procurement, and the delay time. And we're going to also monitor the organization problems. It's an enormous complex scenario here, and our focus is going to be on these four scenarios, where we have scenario 1, where, and scenario B, scenario C, and scenario D. I have put them all in a more precise fashion in this particular sheet. So you have a risk assessment of the site. The scenario is A, B, C, and D. So what does this scenario E means? You have a new reliable plan with backup. It means you have the design of this plant is good, and the maintenance crew is good, and you have a reliable backup. So then you have the scenario B, where you have low customer demand. It means the customer doesn't demand the product, so the plant doesn't utilize its full potential, and so there's going to be loss in terms of plant stop, and there's going to be some routine maintenance. And then you have a scenario C, where you're going to have unreliable maintenance equipment services, and scenario D, where you have unreliable backup, maintenance, and equipment service. So you have everything culminating here. You have unreliable backup, unreliable maintenance, and you have an unreliable equipment services, technicians, or getting the spare parts and all that. Now, coming to the risk, I've been calculating using a very simple assessment which we use it in safety and other environmental risk assessment. Is risk is equal to probability of occurrence into severity consequences. I'm using a similar assessment, so I've given a probability occurrence of failure of a new plant is 0.1. It means I'm so confident, because about 99.99% I'm sure that the new plant will be working. It's working, so it's supplying the product, and I have a reliable backup, so the probability of failure is very low. And what is the consequence of this? Is if it fails, I'm going to lose about 120 hours. That's equal to 5 days in a year. And what is the risk? Is the multiplication of this 0.1 into 120 is 12. Now, for reason for the production loss, why do we stop? Why we have to stop it? Why, if there isn't stop? It could be many reasons behind it. If there's a stop, it's due to routine maintenance. The risk is low. We have set a criteria. If it's less than 100 hours in a year, it's low risk. If it's more than 100 hours in a year, it comes in a high risk, and there is a cost behind it. So there's $8,035 in every hour we'll lose if it stops, if the unit stops, or if the backup has to supply and the backup has to be sourced from outside. So we're going to lose 830 hours, $830 per hour. That's about, here it's about $10,020 we'll be losing if it stops for 5 days. So the risk is pretty low. As you can see, the cost involved is pretty low. Now let's look at the next scenario, scenario B, where we have a low customer demand, low customer demand. It means the customer reduces the demand. So you have a, I've taken a probability of 50%. 50% the probability of this customer not wanting the product. So severity consequences, loss of about 228 hours, that's equal to 12 days. That it means I've chosen one day it stops every month. So 12 days in a year it doesn't produce. The reason being customer doesn't want product. And they have set a criteria here where if the cost is more than $120,000 a year, then it's under high risk. Here high risk is more to do with investment, more to do with because with some money put into it, the criteria can be changed as well. Because this value depends on several other factors, because what is the capital cost, what is the IRR, interest on the return been studied, which been taken for this particular unit, and what is the return on investment we expect. So if you're going to put in this much capital and if it's not meeting, it's not giving back the return on the investment, then it comes on a high risk. So these factors can always be changed. That depends on the unit on which it was the financials have been decided. Now I can go specific into this, but I just put the value here, which can be changed if we had the precise number. Now let's look into the unreliable maintenance and equipment service, which means if some particular part is not working, or if there is one particular equipment which is not, it has to be serviced, we have to either have a planned maintenance, or if it's unplanned maintenance, or if it's a sudden failure, then we need to call the technician. So there's going to be wait time because the site is remote, and there could be other uncertainties involved. Spare parts which has to be sourced maybe from other part of the continent, and the maintenance crew has to come maybe from Germany or from United States, depending on the complexity involved. So probability failure is high. I've chosen 0.7. This values, how do they get it, is depending on the studies we made. We studied on, when we did a stress analysis, we saw the tail end, or how the availability unit drops. I've chosen a lower tail end at the tail end, where we have MTTR more than 40-50 hours or 120 hours. That's the range I've been studying, and I've chosen the availability of the unit drops to about 70% or 60%. So I've chosen a probability of occurrence. It means the failure can be about 0.7. It means the availability is very low, less than 50%. The severity consequences, 10 days in a year, we could have a breakdown. That's about 20 to 40 hours. And the risk is depending on the probability and the severity consequences. So this is due to the waiting time and the repair time and spare parts and all that put together. And then comes the scenario, which is a worst case, where you have an unreliable backup, you have unreliable maintenance and equipment services. So the probability of this occurrence is 0.6. It means it's all these values have been come from the several iterations we carried out in study 1 for reliability, then maintainability and stress analysis, sensitivity analysis, and then I picked this value based on the study in the previous presentation. So what is the severity consequences? You could have a 600 production loss hours in a year, and the risk involved is 360 because this probability is 0.6. This is due to the backup waiting time, repair time, loss to customer, and we have not factored the loss to the customer. The reason is it's complex, and the supplier is more focused on his liabilities, and the loss to the customer is beyond his preview. The reason being, in this particular case, I'll come back to that later, there is a loss to customer, because if the production, we don't supply the product, it's critical to the customer. The customer stops the plan, and they can incur a huge loss. So the cost here I'm included is what the cost the supplier has for the non-supply of the product. We have not factored the customer loss to the customer in this cost calculation. I've chosen about 25 days in a year, which is almost a month. It could have a breakdown. Okay, there's some more complexities involved in this. There could be, problems of accident, because the person has to come in the night. The roads are not to the standards. There's a lot of accident zones around, and the problem of fatigue, problem of manpower, problem of training people, framing or retaining people, and several complexities involved, we cannot model it. What I've done is I've modeled this particular unit because there is a strong engineering base behind this, and then I'm put them all in a nutshell in this table, and I've given a distribution. I've chosen viable. The reason being, viable is a little more precise in terms of finding when the failure will take place. It's more a better distribution to find, and also you can have a control on the beta. If it's less, more. If less, there is chances of decreasing the risk. If the beta is more than 1, there is a chance of increasing risk. And the several factors comes into this picture. I've chosen viable. We could work on other probability distributions as well, but for the moment I've chosen viable. I've defined the viable distribution for new plant reliability. We can have a look at this. Just click on the, as you can see here, I've chosen alpha of 2, a beta of 0.327. This is the viable distribution I've chosen. So it's within the range of about 0.1 to 0.7. 90% is about 0.18 to 0.68. So this is the range we will be working on. So the probability of a failure of a new plant is within this range. But as you can see, the severity is low. The reason being, we have a reliable backup. So you can either work on the probabilities, or you can either work on the severity of consequences. Similarly, for low customer demand, unreliable maintenance, I've taken the a distribution is viable. We can have a look at this, and I've chosen alpha about 0.38, and the severity constant is 288, and the risk per loss hours works out 144, and the cost is about $120,000 to $40. And in case of unreliable backup, maintenance, and equipment services, the probability is 0.6. I've chosen again a viable. Okay, this is what I was discussing with you was on the low customer demand. I've chosen a viable, and I've chosen 0.38, and this distribution for unreliable maintenance and equipment service, I've chosen a viable, but the probability is high. As you can see, it's about, the beta is more, 0.696, alpha is more as well, 5, and which is in the range of about 0.5 to 0.98. So this is the probabilities on which you can have for it's quite a high probability in fact, and the consequence is 240 hours. That's about 10 days of stoppage, and we could have anything from 10.7 to 168 hours to 240 hours within this range. But in this case you can have about 360. That's approximately 12 to 13 days to as high as 25 hours in case of scenario due. And see the distribution is about 9 from 0.6 to 0.9. It's a very high probability distribution, and the failures and loss of hours are very high. You can see the low cost is about $300,600 a year if we have a failure of this time. So what we'll do is we'll do a Monte-Carlo simulation based on the distribution defined. I've chosen this as an output, the risks, loss hours, and the cost as well. Now let's take the worst case. Before I do that, I think I should show you what happens if we have new reliable plan with backup. Let me do the simulation. I go to at-risk, and I've chosen a 500 iterations. I'm doing 4 simulations. So every time it will repeat. To see the consistency of the simulation, I click on this, say OK. As you can see, the mean is about around 46.79 hours. That's the mean. In 90% we should be around 20 to 80 hours. That's quite reasonable. This 180 hours we are talking about within 2 to 3 days, which is consistent with the actual experience we have with the new and reliable plans when they're first installed. Okay, let's take a situation where you have a low customer demand. Let's look at the simulation. There is 125 is the mean, and so the 90% range is between 90th percentile ranges between 50 to 220 hours. So customer with probability varying from with a viable distribution. You could have an output distribution around this range. So we could expect a loss. We can even look at the cost as well. As you can see here, we could have a loss between $50,000 to as high as $180,000 for stoppage of the plant. Okay. So similarly, for an unreliable maintenance equipment service, let's look at the distribution. The simulation says we could have somewhere around 177 as a mean. That's as close as about a week. A week in a year, that's about 7 days. You could have a breakdown. And it will take 7 days to fix it if you have a major breakdown, and that matches with the actual experience as well. Okay, the cost is high. This cost it's on the cost to the production. It doesn't account the cost to the maintenance. We have not factored that in that particular cost. It's only the cost we will incur if there's a stoppage of production. That's the major component, but there's going to be another cost added to this, is the maintenance cost. And similarly, as I told you, for the stoppage of the plant for low customer demand is the cost that we have invested a capital on it, and are we getting the return on the capital? So several factors comes into this picture, and this one is it's only the loss due to production, and we're not factored the maintenance here. This is going to be additional cost to the maintenance as well. Okay, now coming to the unreliable backup, maintenance, and equipment services, we're going to have let's simulate this. So it's 455 hours a mean. That's quite a lot. It's almost more than 20 days. Around 450, it's about, yes, around 15 to 20 days in a year. And as you can see here, 350 hours to 550 hours is almost like 15 to 22 days in a year. We could probably have a breakdown. I mean, where there'll be no production, and the unit has to be stopped and for carrying out the maintenance, or to repair it, or to get source and backup to supply to the customer. And the cost, let's look at the cost distribution. I mean, the simulation for the cost. We could have the loss incurring about $300,000 is to as high as $450,000, and I mean it's about $380,000 to 82. And so there's going to be a huge component here. But as I told you, this is the cost on the loss of production. Does not factor the loss due to the cost due to maintenance, the cost due to source and reliable backup. It doesn't factor the cost to the customer, the loss to the customer, because since our product doesn't reach them, so they're going to incur some cost. So this doesn't factor that. This factors only the production cost. This is the liability of the supplier. All this I'm showing you here is liability. Plus, we need to add for the supplier as well. You need to add the maintenance cost and to sourcing this backup, and you need to add the service technicians who needs to be here for carrying out this unit. Okay, so there's several complexities in a site like this, and you could probably, there are several. I mean, I can tell you from just not the economic point of view, but I can tell you what exactly happens around this plant is you have a problem of electrical supply, the utilities failure, you have frequent power failures, you could have problems related to cooling waters, you could have problem with all the utilities, you could also have a problem with UPS failure, which is it's tremendous stress on the electronic and computer system, because such units, they are highly computerized, and a lot of instrumentation goes into operating such a unit. And you could also have spurious failures of electronic components, which is unpredictable, and there could be problem of due to weather. It could be there could be problem in the failures in the electronic component, which is spurious, we will never know that, because the time to diagnose a failure, it could take maybe a few hours, or it could take a day, or it could take more than a month. And as you can see from the simulation, so it's what best we have done is what we can do to improve reliability and maintainability of this unit, so in turn increase availability rate where we have a control. But there are several external factors coming into picture, which is beyond the scope of the study. Well, with this note and all the results you want, you can just click on the Excel report, and they get the sheets. As you can see, it's getting out several simulations on the same several on the outputs we have been showing to you. Okay, So if you can see here the output, this is the risk. Now this the criteria, as I told you, this has a low risk or high risk, and the distribution of the cost here, and similarly for it's a repetition of what we're doing here. This is again for the next. It comes under high risk because of the customer doesn't need the product, so there is demand drop in the demand, but we do incur the cost because there is a loss of non-producing it. As all this is shown here, and you can see the simulations are consistent. Okay, let me save this as the simulation, risk assessment simulation. Risk assessment simulation. Okay, so this the best what I can do from what I've seen in the field and what my experiences are, and I try to model them and show it to here. But as I told you, the site view is fairly complex, and there are several factors comes into picture, and the risk levels are, as you can see, for the scenario D is very high risk, and scenario C is high risk, scenario B is high risk, and only if you have a new reliable plan with reliable backup, you will have a low risk. The reliability of the plant is a very important factor in terms of risk. So if we could work on the reliability of the plant, and that's what we've been doing in the first 3 slides. We studied the reliability, availability, then we did the stress analysis, and then we did the sensitivity analysis, and we clearly identified the factors of where we can improve and by which we can lower the risk. So with this, I conclude my presentation on reliability studies for a process plant by clearly showing you the risk assessment of the site. From these values are based on my experience and my from the field. It's what realistically matters, but the complexities involved is very high, as I told you from this figure. And but the best we can do is to improve on the reliability of the plant and on the backup, and that's where we can lower the risk. Thank you.